Okay, time for examples. As a first example, let's just take an operator from C2 into C2. So that operator A would then be given by a 2 by 2 matrix. Let's denote its entries by A, B, C, D, which are 4 complex numbers. And let's see what we get as the adjoint of A. I mean, we've done all the computations here, and if we've done everything right, then the adjoint operator that we define in our definition should just be given by the adjoint matrix that you know from your first year linear algebra course. But let's see whether that is true. So again, here's the job description of the adjoint matrix. And now let's fill in the gap to see how everything works out. Okay, let's start from the top. Then compute this matrix vector product explicitly. Okay, and now spell the whole scalar product out. And because we're in complex space, we should not forget the complex conjugate bars on top of the y1, y2 entries. Okay, at that point you might not know exactly how to proceed, and if that's the case, it's often a good idea to walk backwards from the finish line and try to meet in between. Okay, because A is an operator from x to y, we know that A star is an operator from y to x. So in either case, it's also a mapping from C2 into C2, or it's given by a 2 by 2 matrix. We don't know the entries yet, so let's put question marks there. Okay, but that's helping already, because we can kind of see that if you express this scalar product, you get x1 times the first component of the second vector, and don't forget the complex conjugate bar, plus x2 times the second component of this second vector, and don't forget the complex conjugate bar. Okay, so having seen this, let's now again work from here and try to sort for x1 and x2. And of course we find x1 here, leading to this expression together with the y1 bar coming from here. And x1 is also here, leading to this c here together with the y2 bar from here. And then just in the same style, you factor out x2 from what remains, and you get b times y1 bar plus d times y2 bar. Okay, now I think we're all ready to finally close this gap here. So we can almost copy this bracket from here to here, except that we have to get one large complex conjugate bar out. Okay, and that's clearly how it works. Well, if you try, then you see that computing this expression will take you to that expression. Okay, and then do the same thing for this second part of our sum, and we arrive here. Okay, but now by this equality, the first bracket here without the complex conjugate bar on top has to be the first component of this vector that results in this matrix times vector product. And this second bracket, again without the complex conjugate bar, has to be the second component of that product here. Okay, but this is clearly telling us by what we have to replace these question marks. So in this first row of our unknown matrix, we have to put A complex conjugate and C complex conjugate so that they meet y1 and y2 when multiplying. And in the second row, we have to put B bar and D bar so that B bar meets y1 and D bar meets y2 when multiplying. Okay, good job. So we've finally seen that A star is given by the 2 by 2 matrix A bar, C bar, B bar, and D bar, which perfectly fit what you have learned in your first year linear algebra course, that you just have to transpose and complex conjugate your original matrix A to get here. Okay, time for another example that you probably didn't do in your first year linear algebra course. Let's again take x and y to be the same space, but this time infinite dimensional. And because we need scalar products, let's take L2. And our operator A simply be the forward shift. So it takes a sequence and just moves every entry one position to the right, filling the empty in the first position by a 0. And now let's use the same style as in example 1 to derive a formula or even understand what the adjoint operator A star is doing. Here we go. So we again start by the definition or job description, if you want to say so, of the adjoint operator. Okay, and then fill in the little details. Now let your operator A act on the vector x and expand the resulting scalar product. Assuming that we are using complex entries in our L2 spaces, we should not forget the complex conjugate bars here. If you're talking about real entries, then you can ignore these. And now this is again the point where we don't quite know how to continue. So let's again work backwards. And just like in example 1, we again see that we have to multiply x1 by, well, the first component of this expression, and then x2 by the first component of that expression. Okay, again, not forget the complex conjugate bars, but the message is that again we have to sort for x1, x2, and so on. So let's do this from the top. So this is easier now than in the previous example. We just get x1 times y2 bar plus x2 times y3 bar and so on. And now we are already ready to write that as a scalar product with our x vector, and well, we exactly know what to put here. So there is y2 and then y3 and so on. The complex conjugate bars come from evaluating the scalar product here, so we don't have to put them inside. And it seems that there is not much more to be done, so we've already closed the gap here. Yeah, maybe let's close it a little bit. And this vector here is simply telling us what A star applied to the original vector y1, y2, and so on has to be. So we conclude that A star takes our original vector y1, y2, and so on. Let me write it as a row now, because that is what you usually do with infinite vectors, or thinking of as sequences, and maps it into the infinite vector or sequence that we just copy from here. So do you see what happened? The original operator A was a forward shift, so every entry of your sequence was shifted one position to the right. Okay, and now its adjoint seems to be the backward shift, so everything is shifted one position to the left. In particular, the first entry y1 is getting lost. But actually this result is not a big surprise if you look at it from a matrix point of view. Well, this time we need infinite matrices. So let's try to write the forward shift as an infinite matrix. And what we know is that if we apply it to an infinite vector x, we get, well, almost the same vector, but only shifted one position forward, or we could say downward here, and the empty first slot is filled with a 0. Now, which matrix is doing this job? Well, because of the 0 in the top component, the first row needs to be all zeros. And because this x1 in the second component, our second row here needs to pick the first entry of your vector and ignore all the rest. Okay, and the third component in your result is the second component of your input. So that's how you compute the third row of your matrix. And I think now you're getting the idea. So what we observe is we have zeros along the main diagonal, which is infinitely long, of course. And all ones right below this main diagonal, which is also another infinitely long diagonal. Okay, but if that's the matrix representation of the forward shift A, then it's not really surprising that the adjoint of your operator is represented by, well, the adjoint of that matrix, and we all know what that is. It's just a transposed matrix and complex conjugates, which in this case we can ignore because all our matrix entries are zeros and ones and hence real numbers. But in the same style, like we just checked that this matrix shifts every entry of my vector forward or downward in this orientation, then you would see that that matrix is shifting in the opposite direction. Okay, and that's nothing but the result of our previous computation. So no big surprises here either. Okay, let's close this small part about the adjoint operator with a not very long list of properties. And these properties will say how the map that turns an operator A in LXY into its adjoint A star in LYX. So how that map is compatible with the other structures that you have in these spaces, like addition, multiplication by little alphas, possibly also composition of two operators, norm, and so on. Okay, and here's the list of properties. So the adjoint of a sum of two operators equals the sum of the two adjoints. Not very surprising, because you know the same from matrices, of course. Second property, the adjoint of alpha times A is very important, alpha bar times the adjoint of A, well, because you know that taking the adjoint is also connected with taking complex conjugates. Third property is about product, or we should better say composition of two operators A and B, and the adjoint of that product equals the product of the two adjoints, but you have to reverse the order just like you are used to this rule from your first year's linear algebra course where A and B are matrices. Fourth property, the adjoint of the adjoint is A again, also not surprising and also very easy to show. Number 5, the norm of the adjoint is the same as the norm of A. And number 6 is also about the norm, but is a bit more complicated. The norm of composition, adjoint, and A is the norm of A and then squared. Properties 1 to 4 are easy to prove really. Let's do the probably most complicated one of them. So let's prove number 3, and again you start with the definition of the adjoint. So you write down this line here. Okay, and then you think how to fill in the gap. So let me first copy what we just had, and then use the fact that the adjoint of A is the operator that goes here when you move A across the comma. Okay. And now having done that, you also move B across the comma, thereby turning it into its adjoint. Okay, but then you've already isolated your X in the first component. And what you see in the second component must then be, well, the adjoint of AB applied to your Y. So you can argue directly that this operator B star A star must do the same as AB in brackets star, and of course that was our claim. Properties 1, 2 and 4 can be shown in a very similar style. Properties 5 and 6 are in fact a lot more difficult to show. Let's do that in problem 7 on our first exercise sheet.